All right. I'm about to get started today. Before I do, keep in mind if you are enjoying this project and the streams and the archives of the streams, I am counting on people who watch this and who are enjoying it to consider becoming a supporter or a member. Um, I get all of my income right now from people who choose to do that, so it is critical for the ongoing uh, longevity of this project um, and similar projects that I am doing. So before I get started, I have a question I'm going to answer in the chat. Um, can you give a brief description of what you're doing? Haven't watched your videos for a few months. Yeah, so I'm going to tell you about what I'm doing today. I've been working on a project called the Binary File and Object File Deep Dive Project. Um, you can read a little bit about it if you go over to my blog on the membership system. I mention it right here, Deep Dive Project. The whole goal here is to get to a point where we have a much better body of knowledge about how things like executable files work, DLL files, object files that get linked to create executable files, and similarly on, um, I want the same kind of thing on Windows and on Linux and on Mac. I want to have a good handle on these file formats and specifically tools for robustly generating them and diagnosing them when they have issues and parsing them and things like that. And the reason I want to build all of that is because I think that right now we kind of always assume that the thing that's going to spit out one of those files is a compiler or a linker. It's going to be one of those kinds of tool chain type things. And so I think that since I like to imagine a future of the computing world where we're not tied to that ecosystem, I think a very useful thing to do might be to get a really good handle on these file formats, learn how we create programs that run right down at the low level, and start building tools that would let other people who are not doing linkers and compilers, but who just might have their own little ideas, who want to experiment and play, to let them start doing a lot more and see if that unlocks new options for what we do with native layer programming. So I am building out the body of knowledge and the code to go with it that would let us more freely explore that possibility space. Today, specifically, I'm working on a generator for executable files. So I've got Mr. Forth PE gen.c here, right? And this is for generating an executable file. And it works. Like I can build it here. It builds my PE dumper and then my PE generator. And then I can run, this is running the generator, so it just generated the file. And then I can run the generated file and it spits out a 2. And if we want, we can come over here and say like, hey, we actually want to spit out a 7. That'll work, right? So now I rebuild the generator. The generator rebuilds the program. So we are spitting out a program from this code. And when this code it spits out a program, I can then run that program, the generated program, and this is the result we see here. Okay. So I am working on doing a better job of structuring the construction of this. And since I'm trying to structure it, I'm going to answer your question in a minute. I was in the middle of a thought that I want to finish. Since I'm in the middle of structuring it, I had some ideas. I have some like strange new code that I threw in. I threw in these pointers yesterday. I had some ideas. You know what? Let me pull up Milton. We're going to want Milton. I had this idea for constraints and this idea for sort of pointers or relocations or something like that. And so we were kind of pursuing those. And it turns out there's just some problems with how I was building it so far. It's a little overcomplicated, hard to use, things don't line up quite right. So one thing we could do is work on being able to rearrange how we generate these sections a little better. We can also simplify this so that it's not quite as much complexity in specifying these pointers. Although there might be a limit to how much we can do to simplify this. Another thing I thought about doing is going over here and reading about the types of relocations that are actually built into the file to maybe get inspiration for how relocations tend to work. They might have design ideas encoded in this that I could learn from if I study it carefully. So I'm thinking of doing that. Now, to answer your question, Is it similar to this is a follow-up question to what I'm working on right now. Is it similar to Cosmopolitan from Jart? Let's see. I don't know about Cosmopolitan. Let's take a look. Makes a C build once run anywhere language like Java, except it doesn't need an interpreter or virtual machine. Instead, it reconfigures stock GCC and Clang to output a POSIX approved polyglot format that runs natively on Linux, Mac, Windows, FreeBSD, OpenBSD, NetBSD, BIOS with the best possible performance, tiny footprint imaginable. For an introduction to this project, please read the Actually Portable Executable blog post. I think I've seen this before. Yeah, so it's not similar to Cosmopolitan, although Cosmopolitan is cool. Um, so this is cool and it is related. So like this generates a type of file that is carefully constructed to work better than a usual executable, but it also takes advantage of the low-level details of how executables work so that it can work in lots of operating systems, if I'm understanding correctly. But the point is, this is a specific, this would be a cool thing to target, if I learned how to build actually portable executables. That would be cool. But that's not exactly what I'm doing, right? I'm just trying to make it possible to build regular old executables. Now, maybe I'm wasting my time and it'd be better to just build these. But for now, I'm going to just stick with what I've started on. Because this could easily be... This could easily be a rabbit hole that doesn't turn out the way I kind of want it to. And I know that what I'm doing gets me where I want to go, even if it's a longer way around. So this is cool, though. It is similar. This is like messing with the executable format. I am similarly doing that, but I'm not designing a new executable format right now. I am just working with the existing ones on the operating systems. Okay. I appreciate that. Let's think. So I had a lot of bad feelings about this pointer system from before, and I want to read about the base relocations again. Type. The base relocation is skipped. The base relocation adds the high 16 bits of the difference to the 16-bit field at offset. The difference is calculated between the preferred base address and the base where the image is actually loaded. If the image is loaded at its preferred base, the difference is 0, and thus the base relocations do not have to be applied. So we're assuming here that the difference is going to be a 32-bit integer. So here it says relocation adds the high bits. Relocation adds the low bits. Here it says the base relocation applies all 32 bits. I think they mean adds, right? They didn't get specific. They just let us know that it's applied, and we have to Figure out what that means. The base relocation adds the high 16 bits of the difference to the 16-bit field at offset. The 16-bit field represents the high value of a 32-bit word. The low 16 bits of the 32-bit value are stored in the 16-bit word that follows this base relocation. This base relocation occupies 2 slots. The base relocation adds the high 16 bits of the difference to the 16-bit field at the offset. The 16-bit field represents the high value of a 32-bit word. So this is identical to this, except then the low 16 bits of the 32-bit value are stored in the 16-bit word that follows this base relocation. Right? Okay, so the next 16 bits after this are not a base relocation 4-bit 12-bit, they're just a 16-bit so the low 16 bits just get set directly or something. Okay. These things get annoying. Yeah. Okay. So it looks like the main idea here is all these relocations do is to apply okay, let's look at COFF relocations. They might be more relevant. Object files contain COFF relocations, which specify how the section data should be modified when placed in the image file and subsequently loaded into memory. Image files do not contain COFF relocations because all reference symbols have already been assigned addresses in a flat address space. An image contains relocation information in the form of base relocations in the reloc section. For more information, see the reloc section. For each section in an object file, an array of fixed length records holds the section's COFF relocations. The position and length of the array are specified in the section header. Each element of the array has the following format. Virtual address, the address of the item to which relocation is applied. This is the offset from the beginning of the section, plus the value of the section's RVA/offset field. See table section header. For example, if the first byte of the section has an address of 0x10, the third byte has an address of 0x12. Such unclear documentation. Yes, the third byte has address of 0x12, sure, but the virtual address field for the third byte would be 0x12 is what you're trying to say, and you didn't say it. A zero-based index into the symbol table. This symbol gives the address that is to be used for the relocation. If the specified symbol has section storage class, then the symbol's address is the address with the first section of the same name. Symbol table index. A zero-based index into the symbol table. This symbol gives the address that is to be used for the relocation. This symbol gives the address. Symbol table a 0. If the specified symbol has a section storage class, then the symbol's address is the address with the first section of the same name. Okay. A value that indicates the kind of relocation that should be performed. Valid relocation types depend on machine type. See type indicators. Type field of the relocation record indicates what kind of relocation should be performed. Different relocation types are defined for each type of machine. The 64-bit VA of the relocation target. The 32-bit VA of the relocation target. The 32-bit address without an image base. Rel 1, rel 2, rel 3, rel 4, rel 5. So you stop there. I needed a rel 4 before, didn't I? So you're using a type field to encode that there's this. Okay. Section, the 16-bit section index of the section that contains the target. This is used to support debugging information. The 16-bit section index of the section that contains the target. So this lets you say, write down 16 bits here that represents a section number for the symbol. Right, so we could have several with the same symbol. One of them's a section, one of them's a location or an offset, sacrel, the 32-bit offset of the target from the beginning of its section. This is used to support debugging information in static thread local storage. Sacrel 7, a 7-bit unsigned offset from the base of the section that contains the target. Okay, I'm going to write some of these down because this is a little more interesting. So we're seeing here some information that I want to be able to remember. So we have these sections, right, of data. They look like this. They got data on them. And then attached on them are these this table. And so the table has 3 columns. There's an offset. So that's an offset of where the relocation needs to be applied relative to this section. Symbol. And the type. The type is the type of relocation. Let's get snacks over here so that doesn't happen again. Okay. So then what happens is we have various types of relocation, and I want to know about those. So we've got things like here are our types. We have things like adder. That's not how you spell that. Adder 64, which points at 8 bytes. And we fill in the adder of the symbol, right? So let's see. Let me kind of do this as pseudocode instead of as a picture. I think that's going to work a little better. This is going to be like set putter set 64 putter adder of symbol. right? There's adder 64. Here's adder 32. This is just set 32. Putter, adder of symbol. So this one here would be the same as this, except that without an image base. Except that it would be still relative to the image base. So instead of being a virtual address, which is going to have to get relocated, it's just relative to wherever it gets placed, right? So this is like adder 32 and B means set 32, putter, adder of symbol minus base V adder. So each of these, rel 32n, is like rel 32 underscore n means set 32 onto the putter and then we're looking at adder of symbol minus, this is going to be basically the adder of the relock minus n, right? That one's interesting. Section. Okay. The 32-bit offset of the target from the beginning of its section. Set 32 putter adder of symbol minus section base minus the address of the section of the symbol, right? We could use that kind of naming scheme up here for consistency in my notes. This would be index of section of the symbol. A 7-bit unsigned offset from the base of the section that contains the target. That's weird. But okay. Set 7 bits at putter, dittoing the rest. CLR tokens, don't even know what that means. SRL. 30-bit signed, span-dependent value emitted into the object. Span-dependent value emitted into... Don't know what that means. A pair that must immediately follow every span-dependent value. A 32-bit signed, span-dependent value that is applied at link time. I don't know what any of that means. Has anyone done anything other than copy the documentation from Windows? Where is there an explanation? Okay. Maybe I can do this. All right, that's the definition. Can we find... Doesn't mean anything new to me. Here we go. Span-dependent value behavior changes in NPass assembly. The information in this article is applied to Microsoft Macro Assembler version. When the Microsoft Macro Assembler assembles code that depends on the difference between the values of two labels, a span-dependent value, the result of an assembly by MASM version 6 or later differs from the result produced by an earlier version of MASM. Specifically, the difference occurs when the application uses a span-dependent value in one of the following cases. In the expression of a preprocessor directive like if, in the expression of a predefined macro like okay, cause, resolution, avoid using span-dependent value in a preprocessor directive or in a predefined macro. If the code requires a span-dependent value, create and review a listing file to determine that each span-dependent value is evaluated as desired. Avoid using the percent operator with span-dependent value. Okay, so you found a bug, and so that's quite a lot more pre-existing knowledge about span-dependent values. Let's take a note here. I might need to go and ask for help on this part because I'm not finding I'm not finding much chance of understanding this. So we're going to look at these ones. Whoops, not you. These ones here are going to be the ones we are stuck on that we can get help on. Okay. Okay, adder 32, adder 32NB, branch 24, the 24-bit relative displacement of the target. So that's like rel 24. The reference to a subroutine call. The reference consists of two 16-bit instructions with 11-bit offsets. 11 bits. Rel 32, the 32-bit relative address from the byte following the relocation. Section relative, the 32-bit VA of the target. This relocation applies to a MOV W instruction for the low 16 bits, followed by a MOV T for the high 16 bits. Okay, those are interesting. So let's say that that is different enough that it warrants a note. MOV 32 says the 32-bit VA of the target. This relocation is applied using a MOV W instruction for the low 16 bits, followed by a MOV T for the high 16 bits. I don't know exactly what it means by applied using a, but I think that what they're saying is that there's going to be a pair of pointers. We're going to basically have set 16 put her low, low 16 adder of symbol, and then we're going to also have set 16 put her high, high 16 adder of symbol. Same thing. Okay, that one's interesting. So we have branch 20 means 21-bit relative displacement. So a 2-byte aligned target. The least significant bit of the displacement is always 0 and is not stored. This for locations. Okay, so what we're doing is we're setting 20 bits at the putter by taking the low, by taking bits (20) 1 to 20 1 to 21 of the adder of the symbol. Okay, this is the same thing but with a few more bits. Low 2 bits. Cool. ARM REF high, ref high. Okay. So I'm going to stop there for now. There's more processors we could go through, each with their own relocation systems, but I'm kind of trying to generalize here, and I think these two examples are probably the good, relevant ones for me to look at. Oops. Okay, so what I'm seeing in all of these is a couple of mostly simple repeating patterns. The section index part is a little funky, so we'll sort that out separately, but let's say if we look at all of these, and all of these can all be understood in the same way. All right, these are all a set of some number of bits from a portion of bits calculated off of the address of the symbol, the base address of the image, the address of the relocation, and the address of the section that the symbol is in, and some arbitrary n, right? So the components we have here are components. Okay. We've got n number of bits to set. All of these include the address of symbol. Sometimes we have image relative, which means we want to subtract base v-adder. Sometimes we have relock relative, which means we want to subtract the address of relock. Sometimes we have section relative, which means we want to subtract the address of the section of the symbol. Then these three things here all say we also want to be able to say what is the shift. How many low bits? Number of the of low bits to discard from number of low bits to discard from the value. And I think that's everything. So those are the common components, but of course there's a couple I'm skipping here. There's the actual, if we look back at what we originally had, we also have the offset and the symbol index, right? Okay. So let's just see here. I'm going to make a little table. I'm going to try to make it clear. You know, let's change color. That's going to help a lot. Let's change color. And so the number of bits to set, 64 is the max, 1 is the min, so like a byte, 1 byte is enough. This could also even be less. If 64 is our max, let's just say that like 127 might be the max, or 128 even. If we need to be able to do 128 as the maximum value, we could still fit it in 7 bits because we'll never have a 0, right? Or 7 bits if we really want to pack it down. This is 1 bit. This is 1 bit. This is 1 bit. Number of low bits to discard from the value. So that is going to be similar to the number of bits to set, because if we can set, for instance, if we can set 64, then we can calculate a 64-bit size thing, and we can discard a certain number. So 1 byte for 7 bits. Now this is free because these just get stored with their section. This is 4 bytes. And the target symbol, now that's interesting. The target symbol in an object file, it's just an index. For me, I don't really have symbols, and maybe that's why this was hard earlier. If I had a symbol system, then instead of saying putter is this section of data and this offset, I would just be saying here's the symbol, right? It'd be something like that. So we want to say that there's a pointer to this symbol inside of section text at position 2. There's a pointer to this symbol (32 bits). Relock relative, 0 shift. So we have that. These are the bits, 0 shift. Here's the symbol that we want to point at. And there's the relocation offset. 1, 2, 3. 1, 2, 3. Relocation offset. Target symbol. it takes to create a symbol key in that case, I guess. All we end up doing with the symbol is answering a couple of questions, which is what section and what's the offset, which is what we had here, right? So we could say a symbol, something to note here. The point of a symbol key is to be able to get a section index and a section offset. So if we were doing symbols, we would need something like gen symbol right? It would just need to know the section and the offset. And the point of bundling those is mostly because we might have multiple things that point to the same spot. That wouldn't be that would be very typical. And so being able to give that thing a bundled name and pass that bundled name around simplifies the code that you write, and it decreases the size of the data you're moving around through the system a little. So that makes some sense. But what we really mean here by symbol, at least currently, is more like a location, or maybe like a label. Now, to deal with the rest of the weirdness here, okay, that'll make some sense. So the -4 bias, that's the thing I skipped, isn't it? Looking at all of this, I skipped this end piece. That actually needs to show up somewhere too. So let me squeeze it in. Um, Now, I just want to see. So in their system, there's 4, 8, 10 bytes per relocation. In the system I'm proposing, there would be maybe 12 bytes per relocation, but we would have all of them served without using a kind system, except for this one, right? So let's look at that. There would need to be another thing going on. There you go. Like this. So we would need here I think we would still want n for the number of bits to set. How many bit fields have I taken? 1, 2, 3. All right. So we could set aside one bit to distinguish kinds. We could also avoid that and say that there's a bit in here that just says something like, you could imagine if we just played around here, we could say like, hey, sec index, and let that be replace adder of symbol with index of section of symbol. Right? It'd be like that, and then you would go one bit. Right, we just squeeze in a new idea there. Super tiny, but like, you see what I'm saying? Like this would happen, then we wouldn't need to do this. We put that bit there on the table, no kinds at all. They're all the same thing. It's cool. The only thing I'm concerned about is like there still might be weird stuff to come up. Now, a lot of these weird things are just like splits that I would end up having 2 relocations instead of 1 for each one of those. in my system, right? So this one is handled by using 2 relocations. I've used up 4 bits, so I have 4 bits to spare to create a kind system if I absolutely have to. And it still fits in 4 bytes per type. Cool. Okay. I like the idea of that. Let's try this out. So we're talking about basic helpers that let you say, hey, once you've figured out a layout, I want to go back in and rearrange the data in the sections to link things up properly, to handle those relocations of those sections, right? That's the idea of all of this. And so yeah, I'll keep the name pointer. Each pointer is going to need to know its relocation offset, target label. So there's the target label. There's the relocations offset. And then we need num bits. Val shift. Bias, val bias. Image relative. I'm gonna make these small. You know what? I'm gonna X list this. Oops. Image relative 1. Relock relative 2. Section relative 3. Section index 4. Okay. Okay, not bad. Not bad. So, now the question is, we're going to build up the systems of labels. And for now, all a label's going to know about is which section it came from, and what offset it has. No, I don't need that. I just need... Right, so that's how we do gen label. Okay. And then we have to talk about how we do gen pointer from scratch. So gen pointer. We need to tell you what section you're in. We need to tell you what label you point to. Then we need to tell you the offset of the relocation, which is 2 in this case, good. The num bits, which is 32, good. The val shift, which is 0, good. The bias, which is also 0. I'm gonna put the bias before the val shift, actually, because of the way they get applied. No, go away, I want this, yeah. Bias, then shift. Bias, shift, gen putter flags, gen putter And so here we go. The putter, allocate it. Stick it. We stick it into the section. Target label equals label. Relocation offset equals the relocation offset. The num bits equals the num bits. The bias equals the bias. The val bias. The valbius. Val shift, val flags. So we put val flags first, probably, in case that gets used as a kind. We could also say 4, 5, 6, 7 here, so that the first 4 bits, the low 4 bits, will be the ones that work as a kind. So we're just assuming those are zeros for now. But if we ever want to, we can say, hey, this was all what happens when the first low bits are 0, but we have 15 other kinds available to us to expand out other ways these bits can be interpreted. Hopefully that's enough to get us wherever else we need to go. Or else we can expand this too. It's still under development right now. It's not... no final decisions about what to shift have been made. About what to ship have been made. But a little bit ago, my alarm went off to remind me to take a break. So I'm going to wrap up as soon as we are looking at errors in the creation or application of the gen putter. I'm going to take a break, I mean, not wrap it up. There we go. All right, from there, I'm going to take a 5-minute break. When I get back, I will resume from here. See you in a minute. All right. Here we go. This is the code right here that applies a gen putter. Let's get serious about this. We're going to have to calculate the value. The value is going to be a 64-bit integer for now. Let's start with if gen putter val flags and gen putter flag sec index does not equal 0, then val equals. We need to know the section index. We don't have a way of doing section indexes yet. Section indexes. Val equals the address of the target. So we're going to go in here. We're going to grab the target from the gen putter. The target is going to be contained in some section. So we're going to figure out the gen section target section. Target gen sec, which is going to be target section. Then we're going to need the layout section, the target laysec. Here we have to do a loop that we've already done in the previous iteration that we still want to get rid of. Target laysec equals the check laysec. What are we doing here? The layout j. Okay, we'll check if that equals gen putters. Target gensec. So if we find the target gensec, then the check laysec is the target laysec break. That makes sense. So this is the target laysec layout section voff plus the target offset. There we go. Done. All right. That's how we calculate the address of the target. Next, we need to calculate. Okay, if gen putter val flags and pe gen putter flag image relative does not equal 0, then we're going to add in, subtract out the image base vadder. Do we have that? I mean, we don't know that yet. Layout image base vadder. Let's add that to the layout. We'll just have the layouts calculate that. As a new thing that they do. Okay, let's go see about the layout. Layout image base vadder ox14. Yeah, this one right here goes here. Layout image base vadder. We'll get to you. Back to gen putter. No. Back to the loop. The loop. There's like a loop. Show me the loop. Yeah, this one. Okay. If gen putter val flags and the pe gen putter flag for relocation relative does not equal 0. Address of the relocation. Okay, so the relocation is the gen putter itself. The gen putter itself contains in it information about the current. We know about the current lay section, so this will be val minus equals the current lay section voff plus the gen putter's relock off. So that's the address of the gen putter, the relocation location, right? The relocated thing, that's its address. And if gen putter val flags pe gen putter flag section relative does not equal 0, the address of the section of the target. So we want to subtract, in that case, the target laysec v off. So that's all the flags. Then what we want to do is we want to val plus equals sign extend gen putter val bias. Finally, val equals val shifted by the gen putter val shift. Okay. That's our value. Okay. That took a lot. That took a lot out of me. Okay. What's next? So once you have the value, what do you do with that shit? You gotta put it somewhere, right? The relocation off tells us where we're writing it. The number of bits tells us how many we're writing. So something I didn't do is I didn't allow you to shift the, so there is a flaw here. I can give you an offset into a section by number of bytes and say this byte here is where the relocation begins. But sometimes it's going to want to be a few bits into it. Like if we have an instruction where there are 16 bits, several, like it's, somewhere in there's 21 bits or whatever for all those. Remember this? I'll just show you the picture again. Fuck. It's like right here. This nonsense we were looking at, right? 20 bits. That might be the small 20 bits, but if it's an instruction, probably there's a few bits at the beginning, and it's probably like a 32-bit instruction. And so the first 12 bits are telling us what type of instruction we have, and it's going to be like the high 20 bits at that target location that we actually mean to set. So it's probably going to take another byte to encode that. The val shift tells us what portion of the value we calculate to keep. We need another one that's like a relock shift, right? It would go like right here. And so basically we would load in the gensec data plus the gen putter relock off target size. So we load in the existing version of the value. So what are we thinking here? There's like I'm not very good at this kind of thing, treating them. Okay, so what we're doing here is this 64-bit integer is a local variable in my function. I'm treating it as a buffer, so I filled it up with the data from the actual memory buffer that contains the thing we're trying to relocate. And I'm doing that because I need to do a bitwise operation that modifies some of the bits in this little bit buffer that I've got, right? This is our bit buffer. And what's going to happen is that there is some low bits here, right? And so we have some low bits that we don't set. We want to keep these. We want to keep some number of bits, and then we're going to modify some number of bits, and we're going to keep the rest, right? Now we have the number of bits that we want to modify. That's num bits. We have how many bits we want to skip over at the low level, or at the beginning. That's relock shift. So this would be if there were 4 in the relock shift and, you know, whatever this is, like 15 or something in the num bits. And the question is, what is the right way to set the bits on a bit buff like that? I can try to form a mask. I can So I guess what I can do is this. How do you do this kind of thing? Like, okay. The high part is bit buff shifted down by the relock shift plus the number of bits. The low part is the bit buff shifted up by the number of bits plus the number of high bits. Right, okay, hold on. There's like high bits equals low bits equals gen putter relock shift. Mid bits equals gen putter num bits. High bits equals 64 minus mid bits minus low bits. And so the high part is the bit buff shifted down by low bits plus mid bits. Which is low mid bits. The mid part is the bit buff. No, is the val, right? And the low part is the bit buff shifted down, shifted up by mid bits plus high bits. Shifted back down by mid bits plus high bits again. So it goes back where it started, but those parts are zeroed out. Oh. This is so sloppy. I need to... Master bitwise manipulation of... Alright. We need to practice that sometime. That's something I should get good at if I'm going to be doing... stuff with somebody. Well, it's just a thing that comes up from time to time, you know, when you're dealing with files and pointers and offsets and things. And so finally, our result let's call it final, is the low part together with the mid part shifted up by the mid bits, together with the high part shifted up by the mid bits plus the high bits. Mid high bits equals mid bits plus high bits. Mid high bits, mid high bits, mid high bits. Is that even correct? I don't know. And then finally, we want a memory copy into the destination from the final. And you are a PE gen putter flag relock rel. Okay. We're gonna need a little remedy. PE gen. Okay, here it comes. We are going to take a look. The val we got, 4094. That makes sense. 4096 would be a 4K difference. me see one thing. So these are all off. Label, flag, relocate relative, starts at 2. Label. Okay. I think the val flags are supposed to go first. Let's go check that. Relocation offset, number of bits, val bias. Okay. So the val bias is -4, right? The val shift is 0. This should come after the relocation offset. Yeah. Gen putter. Label 2 flags. Num bits. Okay. Okay, so 4096 is the distance between them. Doesn't seem quite right. Let's take a look here. Val, that's the target, 8,192. V off here is 8,192. V off is 0. Image relative, no. Relocation relative, yes. V off, 4,096. Relocation off is 2. So we end up subtracting down to 4,094. And then we subtract out the 4 for the bias. Okay, 4,090 does make sense. No shift in the val. And then we read in the bits. Number of low bits. Number of mid bits. Number of low mid bits. Number of high bits. Mid high bits. The bit buffer that we loaded in is a 0. Mid part, low part, final. Okay, I did it wrong. This should be shifted up by low bits, and this should be shifted up by low mid bits. Mid part is 4,090. We should get 4,090. We write that in. And okay, I think that did it. So boom, boom, boom. There we go. All right, that's better. That's a more real system. I need to get better at this part. And need to build in section indexes. Fix the section indexing problem. Don't need this. Need to tighten up the way to call this because it's a little bit, you know, we got 1, 2, 3, 4, 5, 6, 7, 8 parameters, and a bunch of them would actually fit. We also are missing relock shift now. Interesting. We might just say let's not pass those as parameters. Let's make wrappers for different types of genputter calls, and then provide some defaults. And if you want to, you can extend the genputter call helpers yourself with your own style of generator pointers. The label system looks good. I don't mind that. Okay. So we did this, but we were left with these questions. I'm going to go and ask those around the Handmade Network Discord today and learn a little bit more about those. But I think this is a good place to stop. I think that this is good. So I like the genputter system better now. It feels like I actually built one that like handles a lot of cases, and we did that by looking at some real-world relocation concepts, and then generalizing that to a formula that I think just covers a lot of all the usual stuff. Think we can just drop this. Still want to do this. Still want to do this. Okay. I think this is a good place to stop. So, with that, we've made a good chunk of progress today. If you're excited to see me finish this project someday, I am funded entirely by viewers and supporters of the lab projects. So whether it's my Twitch streams or the YouTube videos I put out or the projects I'm working on, or if it's because you want one of the perks, consider becoming a supporter or a member, and that'll keep it all going. And do check out these perks. There's like the indexed video library is really cool. Getting access to the source code as I'm working on it. Plus you can check out my devlogs every week and stuff. So take a look at that. It means a lot when people do, and I will see you all around the internet. Bye.